All right, let's get started, everybody. Settle down, settle down. Everybody's all excited about the curriculum changes, but relax. Hold on. But, like, you ought to try some Tai Chi, you know. What did he say?
One in the chamber. Tai Chi, Chai Tea.
So, in the midst, hold on, guys. Guys, you realize in the midst of all these curriculum changes, I don't know if you realize, we have an exam on Wednesday. Oh, yes. No, I think I need to use the word exam so everybody's like, oh, we have an exam. Because, I mean, everybody's all excited about the curriculum and whatnot. It's like, guys, I got to bring it down. I got to crush your spirits.
That's why we put
That helps me see, like, for future semesters, like that was the day that we did the exam. Because I can scroll through it real quick.
Is it blue?
Don't start with that. Don't start with that. All right. Let's handle some business. First off, homework 7. Do I have everybody's homework 7? I need them now because I'm giving you the solution right now. All right. Does everybody do I have them? We'll figure something out. No, I'll work with you. That's slightly more important than reinforced concrete design. Slightly, just a tad.
Can you slide that energy for hydrology? About 2 magnitudes more important.
That was sarcasm, everybody.
Did we include some problem too?
Self.
For the dead load?
I don't remember.
You deserve that one.
Hang out for a second after class if you would, all right? Okay. All right. Settle down. Does everybody have a homework 7 solution that's being distributed as we speak? Yes. What's up? What's up?
Problem 2, it says N is 10, but on here it says we have to do 612, and it says for 612 N is 8.
Yeah, but for 612, it's sand lightweight concrete.
Oh, okay.
Sand lightweight, that's a good question. The sand lightweight concrete is going to have a different E value. And so because it's going to have a different E value, it's going to have a different N value. That's okay. Should be 10. No, it gave you the N value for normal weight concrete. Remember, think about it. How do you calculate N? You take E sub S and you divide it by E sub C. Using a different weight of concrete, you're going to have a different E sub C, so you're going to have a different N value. For normal weight concrete. Because the first part had normal weight concrete.
Oh, yeah, you're right.
So everybody got that wrong?
I got it right. It's wrong.
No, and I'm gonna push back on that one a little bit because that one everybody should have caught. So.
I saw it, but I'm like, I don't know what I do with this. So I just didn't do anything.
You could have asked.
I started it too late.
See? Your words. All right. Did everybody? All right. Hold on. We got to make sure we're clear on business. Did everybody get a homework 7 solution? Okay. Here is homework 8. I'm assigning homework 8 today. It's not due till next Monday, and it is incredibly short. So it's just 2 development length problems. Well, that one, I didn't say, no, that one was a long homework. This one's short. I'll admit that one was a long homework. This one's short. Depending on how you write, yeah, you could probably do this on 1 sheet of paper. I'm
Half a piece for me.
like a postage stamp, probably. I didn't say that. Yes, I did. There you go. I need your homework 7, Mr. Foreman. Go ahead and set that over there. All right. So I also need to pass out the exam review slides. We're going to go over those here in a second. 1, 2, 3, 4, 5.
I gotta figure out how.
Okay. So there should be 3 handouts that you all have. You should have the homework 7 solution. You should have homework 8. And you should have the exam 2 review slides. Let me do this. Let me go through the exam review slides, and then you all have the solution. You can ask questions and all this. We'll just sort of save all the questions at the end. Gives you all the most time. Okay, so here's this, the rundown on the exam. The exam is going to be on shears and deflections, specifically on homework 6 and homework 7. Again, I'm not putting homework 5 on the exam. So the exam is going to be closed book and closed notes, but you're allowed a formula sheet. You're allowed a calculator, obviously. The formula sheet, 8.5 by 11. Put whatever you want on it except for worked out examples. Okay? Try and be on time. We're going to start the exam at 9:55, just like we did last time. And I think we're in agreement that we can go until 11:30. Am I right? Okay. You'll have scratch paper. You'll have staplers. Make sure that, or one thing I'll say, anything that's tabulated, like any tabular data, you'll have. Although I'm not really sure what all you would need for this exam, maybe some rebar charts and whatnot, but any of the tabulated data I'm not going to make you memorize or put on your formula sheet. Here's the long and short of it of what's going to be on the exam. So shear, okay? So make sure you generally understand, how shear behaves in concrete beams, concepts, mechanics, etc. Make sure that you can compute the capacity of a beam in shear, VBC plus VBS. Make sure that you can construct the shear diagrams. You also need to highlight the 3 regions. Remember, regions where you need stirrups, regions where the concrete carries the shear, and regions where you don't need stirrups at all. Make sure you can identify those. And make sure you can determine stirrup spacings and layouts. For serviceability, make sure you can identify the reasons why we have serviceability limits in the first place. Make sure you can compute effective moments of inertia. Okay? This also includes the computation of cracking moments, gross moments of inertia, and cracking moments of inertia. So make sure you can do all that. And make sure you can compute deflections based on instantaneous and long-term effects. And that's the exam in a nutshell. As for formulas, for shear, I'll be honest, there's really not a whole lot of relevant formulas. You've got PVN is PVC plus PVS. V is 0.75. There's your concrete capacity and shear. There's your steel capacity and shear, and that's about it. For the design, however, you've got your maximum stirrup spacing increments, required stirrup spacing based on a given shear value. Remember, the VU star is the shear at x equals d. You've got your 3 regions, anywhere where it's greater than PVC, between PVC and half of PVC, and anything less than PVC. For deflections, you've got your effective moment of inertia, and then your deflection calculations. Remember, you cannot calculate live load deflection by itself. You have to calculate dead plus live, and then dead, subtract the two. And again, the reason why is because each of these two quantities has a different moment of inertia. That's why you can't just compute live load. You could just be able to say, what's the live load deflection computed directly. Long-term effects is your immediate effects adjusted by a multiplier. Your rho is AS prime over BD, and then that comes from your temperature effects chart, which, I will do that if you need it. And then your total deflection is as follows. And then there's your time factors and your deflection limits. That's it. Okay, so what I'm going to do now is shut up and let you all ask whatever you want for the exam. Okay, so the floor is yours. Yes, sir. Now, let me say this. So the question was, are there not going to be any doubly reinforced beams? Here's my answer. I can put a doubly reinforced beam on the exam, but that does not mean you will compute Fmn for that beam. What that means is rho prime, and that's it. So no analysis or design and flexure of T-beams or doubly reinforced beams. I can put a T-beam on there. I can put a doubly reinforced beam on there, but I'm not going to ask you to determine Fmn or design for moments. I'm not doing that. Regardless if I put a T-beam or a doubly reinforced beam, the target of this exam is shears and deflections.
For D on rho prime, is it the distance from the top rebar down to the bottom of the beam? Or is it
Yes. Because BD is essentially the effective area in concrete of the beam as a whole. So BD is essentially how much concrete you're providing, and then your steel, how much steel you're providing. And that would not be accurately measured by BD prime. So no, that is right. It is BD, not D prime. Yes?
You have doubly reinforced beams on shear.
Yeah? But how would it affect things? I'm asking you. No, I'm asking you. You're right. It doesn't. I mean, your concrete capacity in shear is 2 lambda BWD square root of FC prime. There's no D prime anywhere, so it really doesn't matter. So, yeah, doesn't matter. Of course, I could put it on there just to mess with you, so, because I'm a nice guy. Yes? No. From the tensile steel, yeah. It's still the same D that we calculated before. Okay. No, but that part, or just?
Could you put T-beams on shear?
Yep, I could. And how would that affect things? I'm asking you.
I don't even remember.
BW is the width of the web. That's the only thing. All right. Let me go through the homework real quick. So on problem 1, you have material properties, pretty straightforward. Beam properties, you have a beam that's 16 inches wide, 32 inches tall. The effective depth is 27.5 inches. It's 18 feet or 216 inches long. The modular ratio is 8. Now the area of steel at 6 number 11, so it's 9.37 square inches. Gross moment of inertia and extreme tensile fiber distance as follows. So the cracking moment's pretty simple. It's Frig over YT. And then our transformed section, it's the same thing that we've done before. You can go through and solve that quadratic expression. You should have gotten an X value of about 12 inches, something about like that. As for your moment of inertia, I have here a note that you can compute it the exact same way as before, and even though the beam is upside down, the steel is up top, it doesn't matter because the calculation is still the same. So all your distances are, it's still the same stiffness. So you should have gotten a crack moment of inertia of about 27,000 inches to the fourth. And the instantaneous deflection, it was asking for the instantaneous deflection due to dead plus live loads. So dead plus live loads, okay. You have a dead load of 2 kips per foot or that many kips per inch, a live load of 20 kips. That does not mean take that live load and divide it by 30 feet. That is wrong, okay? That is wrong. A beam with a distributed load will deflect differently than a beam with a point load on it, just right there. So if you converted it to a distributed load, that's wrong, okay? That is wrong, all right? Your effective moment of inertia is, again, something like 27,000, 57,000 square root of FC prime for E. And then your deflection, you just take each component individually. So WL to the fourth over 8EI and PL to the third over 3EI. Why are those formulas being used? Because it's not simply supported. It's a cantilever, okay? Cantilevers behave differently, so different formulas. Should have gotten about 1.14 inches, okay? Now for problem 2, what I decided to do was, if you go to the very end, here's everything. Okay, so there's the dead load, the dead plus live, the dead plus sustained live, the live load, the sustained live load, and then the total. Okay, now there might be some slight variations in the answer depending upon what you use for the 4-year duration factor. I used 1.9 because I told you all to round to the nearest tenth, so I went with 1.9. I would understand why you went with 1.8, which would change your answers a little bit. So I'm fine with that. Also, the book decided to go off of an older methodology for the transform section where they use 2n minus 1. So if you, and one of the things about the solutions manual, it just tells, I know the solutions manual is, I know it gets distributed, I'm aware. But if you use it, it just tells you the moment of inertia. And that's, there's a lot of work that has to be done just to get that. And if you use that value, it would be wrong. So even if you went with the 2n minus 1, I think there's a typo as well. So yeah. Let's see. Let me go back to the beginning. Okay. So back to the beginning. Number 1, okay, so the material properties, bless you. You've been given a unit weight of concrete of 120 pounds per cubic foot and a lambda of 0.85. So right off the bat, you should have a different F sub R. Let's see. Here's your beam dimensions. Your length is 30 feet. I've got the area of steel and the area of steel prime. Let's see. Dead load and live load accordingly. Let's see. So gross moment of inertia, pretty straightforward. Cracking moment, you should get about 51.6 foot kips for your cracking moment on problem 2. Okay. Now your transformed section analysis, it's the same formula, but for the compression component, you got to add a different component. It's the area times the moment arm being x minus d prime. So that's where that comes into play. And then your area is not NAS prime, it's n minus 1 AS prime. Let's see, what else? Oh, to get in, because it's a different concrete, here's your modulus of elasticity for steel. For concrete, it's 33 times the weight raised to the 1.5 times the square root of FC prime.
Didn't that give us like n equals 8?
Hold on. Now, hold on. Okay. Couple things. One, it said n equals 8 for normal weight concrete. This is not normal weight concrete. All right. How do you compute n? You take the modulus of elasticity for steel, the modulus of elasticity for steel divided by the modulus of elasticity for concrete. It's a different modulus of elasticity for concrete because it's not normal weight. If you go, hold on. If you go back to your notes.
In the problem statement it said n equals 8 for normal weight concrete.
Yeah, this isn't normal weight concrete.
But it gave us not normal weight concrete.
Yeah, it said, Nice try. Now, if you recall, this was in the notes. What's that? Oh, yes, I did. This is not fake news. This is in your notebooks right now. It is on slide 56.
Oh, yeah, I believe it.
2 weeks ago.
That doesn't change anything. Hey, I didn't do this on an exam.
He speaks truth. It's there.
Oh my God.
Yeah. You're right. I stuck into every one of y'all's apartments last night and inserted it into your notes.
And that's recorded.
I'm going to have to dump this recording and redo it. See, it hasn't uploaded to YouTube yet, so.
I think it's some type of like disappearing ink, only the opposite effect where it's not there immediately.
Man, if I could invent that, maybe I wouldn't be a professor because I'd have a lot of money for that.
So if you make money, you don't care about it.
I'm sorry you had to find out this way. No. Funny stuff. But look, I am going to push back on that a little bit because it was here. It was in the notes. Okay, so I'm not going to dock you all substantially, but that was there. You know.
Is it like point system when you make a mistake, like 0.25 or like 0.025?
Have I never, in all honesty, have I never not been fair? Okay, all right. Now hold on. Getting you all to go back through your notes and look through the specs and whatnot, that's my job.
This problem statement does not explicitly state use any.
Hold on. Let me quote something the way you told me once. It just you gotta use your nut.
It just says use n equals 8 for 6, 11, and
Problem has normal weight concrete.
then so when 14 says go back to 12, I'm like, okay.
But you all should have recognized that if the material changes, then the modular ratio should have changed. Oh, now hold on. I did not. Hey. Hey, I didn't do this on an exam. Don't.
Sand weights a little bit.
What's that? All right. Is that? I mean, does everybody understand? Does everybody? Okay. All right. Okay. Now, if you go through and compute your stiffness according to the provisions that we've described, you should have a moment of inertia of about 11,800. So you've got now let me show you what I did for deflection calcs. I did dead loads, dead plus live loads, and then dead plus sustained live loads, and that's how I computed it. So you'll notice with each m sub a, the moment increases. To determine the live load deflection and the sustained live load deflection, just subtract. So once you get those key values, you can do your long-term effects. And again, it's B times D. Okay. So your modifier for dead load should have a 2.0. This one, it could have been 1.9, 1.8. I'm easy to get along with there. I mean, if you had 9.6, there'd be a problem there. But I do expect there to be a little bit of variation with this quantity right here, and I'm okay with that. Here is the summary of what you should have gotten for your deflections.
Maybe I'm wrong. I don't know. But this was on a doubly reinforced beam, and we won't have that.
What?
No, we won't have that. We won't have
I'm not making you do, look, if you go back to homework 5, you had to compute phi for T-beams and doubly reinforced beams. I'm not making you do that. And say I wouldn't put a doubly reinforced beam on the exam. What I'm saying is that you will not have to perform homework 5 calculations, bless you, on this exam. That's what I'm saying. Absolutely.
Like, the only place that double reinforced would affect is from beyond road prime.
Yeah.
That's okay.
Yeah.
So then also calculating all the stuff at the beginning, we have to calculate double with the compression steel and the block, you know what I mean?
Yep. Yeah, you're all right. But I do, let me say this. I do recommend that you all really read the problem statements. So,
So Rich, why is
I don't
before we
think
start?
that's great price.
I read it like 3 times and still messed it up.
So you say you would give us the tabular stuff, and then you have the time to vector graph on the last page. So that we have to copy that down.
no, I will give you that.
That's not.
I'll give you that. That I'm not. Come on, I'm not. I wouldn't do that to you. Okay, I'll do my best to draw it out, and it's gonna be pretty bad.
Where does it apply?
It's just for compression steel, and that's all it is. The idea is this: is that you have a beam, right? So this is B, and that's X, right? And you've got compression steel right here, right? Okay. So you are removing that steel and replacing it with an effective lump of concrete, right? Okay. So what I'm saying is that if you remove it, you now have a piece of concrete with a hole in it, right? So this area would be BX minus, what, AS prime? All right? And then you are adding to that a big lump of concrete that's AS prime. Yes. You're adding, I mean, it's up here, but I'm just putting it down here, okay? Yes, that's what it is, yeah. So what I'm getting at is this. I'm saying that, I had to mark through there. Just bear with me, okay? I'm saying that you are removing that steel and replacing it with concrete. So I'm saying the area of this box right here, the area of this shaded box, is BX minus AS prime, right? Then plus this. Sound good? Okay. So if I wanted to look at the total area in compression, it would be BX minus AS prime plus N AS prime. Would that be a fair statement? Okay. So what if I do some factoring? BX plus a quantity times AS prime. What would that quantity be? That's it. It's just to not double count the area. Like, that's it. Does that make sense to everybody else? This is important. Okay. No. Just engraved the screen. Seriously, all right, we've got time, so I really want to address any question. I don't want the exam to be complicated because there were questions that you didn't ask. So please, anything on shear, anything. I mean, I know we're talking a lot about deflections because you all just turned that homework in, but shear's on the exam as well, so.
Are you going to give us the same, like, use two patterns?
Yes. Yes. I will tell you in some fashion or another how to lay out the stirrups. I want one increment or two increments because I get 30 different answers that would all be right, you know. So.
That means you're putting the design on.
I didn't say that. You don't know. Not for fee M in.
Not for fee and then, no, just like we had a reinforced. We had to do some sort of. It should be
Yes.
So that's a possibility.
Yes. That's a possibility. Let's talk conceptual stuff.
What kind of conceptual questions do you have?
Good one.
That's the wrong question.
Then you come up with one. You just had to write
Guys, please, guys, no confrontation. No confrontation.
Let me ask Joe.
Let us talk.
How many questions are there?
Guys.
Let's do it on the shear. That's gonna be the first question.
A good one. Enough.
Why do you need that 2-inch spacing?
There, all right, okay, so the question was, why do you need the 2 inches at the beginning? There's no structural reason. It's just typical to develop an easy spacing pattern and to get your first increment started. There's no structural reason for it. It's just convention.
Would it prevent like weathering, stuff like that?
No, I don't even think it really has anything to do with that. It's just how they're laid out.
For those terms, like you done homework, are we gonna be able to have multiple answers, or are you gonna give us like guidelines saying?
That's what I was saying earlier. I don't want 30 different answers on the exam. So I'm going to, for the instances that you are talking about, there is going to be a restriction such that everybody should arrive at the same answer. If it is dictated as such. One thing I will also do my best to promise you is that done correctly, I'm going to try and avoid problems with rounding. I'm going to do my best on that. So it's tough on this stuff. It really is. So, but I'll do my best. Yes.
You use 0.75 because it's like a rapid failure, I guess.
Yeah. And the failure mechanism doesn't really change much depending upon the dimensions of the beam. See, if concrete beams get deeper, they're able to develop more strains, so your phi value can change. It's not really the case in shear. So, but yeah, I mean, when concrete and shear goes, it goes quick. So, that.
Yeah, so if you were to ask that question, say, why is it 0.75 instead of 0.9?
But that right there, that's the wrong way of looking. Hold on. What is the phi for beams? No. What did you say?
It's a range.
It depends, right? You're saying phi is 0.9 for beams. I'm saying that's wrong. Phi is not 0.9 for beams. Phi depends.
For shear, all reasons 0.75.
Because of what I just said, with beams, when the dimensions of the beam change, you can get different strains in your steel. Okay? And remember, phi is a function of the strain in your steel. That doesn't really happen with shear, though. You tend to get the same behavior in failure. It's largely independent of the dimensions. In other words, concrete beams that fail in shear, when they fail in shear, they tend to all fail the same way, regardless of dimensions. That's what I'm getting at. That's why it's constant, not variable.
It's still smaller than usual, though.
Well, yes, that is true.
I don't think you're gonna ask that.
Yes.
For example 14,
Hold on.
you may have to pull up the example to understand what I'm talking about.
You said example 14. Is that what you said?
Example 14 where we had distributed load and point loads for shear.
This one.
Yeah, in the shear diagram, we had two different equations to use.
Yes.
We only picked one to determine x. Why is that?
What was that? I don't understand. Wait.
I'll show you. We had two different equations.
Okay. Okay. All right. I get what you're saying. Okay. So, let me pull up the notebook, and I think that'll clarify. Bless you. All right. The general answer to your question is why did we use one equation versus another when we were trying to find points on the diagram is because you can't just look at the equations and go, oh, well, I'm automatically going to use that one. It's not that simple. What you've got to do is look at the shear diagram. You've actually got to look at the values and see what's going on. For instance, what was that? I'm going to have to find this in here. I think this is about it. Okay, so here's our shear diagram, okay? Now this first range here, this is equation 1, this is equation 2. Equation 1, 68 kips to 44 kips, okay? So if I'm trying to find a value of, let's say, 61.33, I'm going to use this equation, because if I know that this equation goes from 68 to 44 and I'm trying to find this value, I'm going to plug it into this one, not that one. Because the diagram shows me, I mean, here's the plot. It's going to be somewhere right here. Do you see what I mean? Yeah. That's essentially it in a nutshell. For these values here, we use the second equation because the equation was valid from 24 to 0, and we were looking for values like 16.43 and 8.22. So I know it's going to be on this range. In other words, I wouldn't use this equation to solve for these values because if I trailed that out, it'd be all the way over here.
Okay, so it just depends on the region you're looking at.
Exactly. Yeah. You can't just look at the equations. You have to actually look at the diagram and the values and go, okay, that's my range.
All right, that makes sense.
What? Oh, okay. Let me pull that out of the slides. It is not because of 45.9. Well, there's probably, actually, there probably is some logic to that. There's something that goes along with it. The main idea is in these close regions right here with these close regions right here, okay, so you agree that if I've got some loads right here, I've got essentially a large point load right there. That's what a reaction is. It's a large point load right there. In that region, we're not really concerned with shear as much as we are bearing forces. In other words, if I have a large, couple thousand or 10, 15,000 pounds right here, I'm worried more about the concrete crushing right here than I am about shear failure of the beam as a whole. That load, it takes some time to propagate throughout the section, okay? The way that ACI handles that is they say, you know what, we'll give that bearing load a little bit of room to propagate throughout the section before we say, okay, now we need to start designing for shear. And the code says X equals D is a reasonable value to go off of. The behavioral reason is because it gives those bearing forces time to propagate throughout the section. That's about the simplest way I can answer it without getting into contact stresses and funky stuff from there. Does that make sense? I guess one way of looking at it is, you know how when you're designing like foundations, like you have your square foundation, but then you have that projecting width, you know what I'm talking about? Kind of the same idea. Kind of the same idea. It's almost like that load is projecting out a little bit. Anything else? You all were so excited about these curriculum changes, and then I came in and said, we have an exam on which I didn't even use the word celebration. I said exam, and everyone went, oh. Anything at all? That came out of nowhere. Where did that even come from?
I'll just be a smear on the floor.
All right, any questions at all? I mean, I know the end of the semester is probably starting to, you know, hit like this. So I hope you do. I mean, you got a couple more hurdles, man.
At this point, I just gotta kick it, kick the ball.
I'm trying to just make sure he does well. He can't just give up now. All right. I'm able to read between the lines. I get the feeling you all are running out of questions. I do want to give you, though, that one sort of penultimate last chance if you've got any questions, because, again, I want you all to do well on the exam. So anything that's on your mind about the exam, like, now's the time. So well, we've still got about 8 or 9 minutes or so. So anything at all.
For stirrup spacings,
All right, hey.
we round down, right, to be more conservative?
Yes. If you calculate a 4.4-inch stirrup spacing, you don't round that up to 4.5 or 5, you round down. Because, bless you, smaller stirrup spacings means more stirrups. More stirrups means more capacity. So it is more conservative to round down than it is to round up. It's important everybody understands that.
Show how to do the calculating the moment of inertia when you have the compression steel.
Okay, I can. The best example, though, is in the solution. It's actually fully. Yeah, I put this in here. That's what. Yeah. Is there a specific part about it, the air or the distances, or?
Yeah, I guess I was just confused on where exactly the compression steel was when you were trying to solve out the moments, like solving for x.
Okay, all right. So if I look at this image right here, okay, this image, when I sum moments, I'm summing moments about this line right here, right? So for instance, if I'm talking about the concrete block, if this distance is x right here, then this distance right here, if that's the center of the concrete block right there, that is x over 2, right? That's that moment arm. Make sense? This moment arm right here is d minus x. What I'm saying is that this moment arm from there to there, that is x minus d prime. Because that is x from the entire height, and then I'm taking off this distance right here.
So that would be the,
And that'd be d prime. What?
that would be the 2.5 inches.
Yes. Does that? Does this make sense? Is there anything else? No, this is important. I mean.
No, it's the whole problem too is bad, but that's good.
You really need to add
The concrete? Yeah.
Oh yeah, I'm totally spaced on that.
I mean, it is a concrete beam.
It's made us.
We only care about the reinforcement. You're like, Dave,
They won't notice.
Listen up for government.
That's how it is. Yeah, just believe me. Yeah, just sand, no water.
We did get like 8,000 something, so that makes sense.
All right. Anything else?
What's your favorite color? Blue, right?
No. We're gonna no.
Is it green?
We've already had this discussion.
For the bonus question.
I remember it being blue.
Bonus. What's a bonus question?
Bonus point.
What are bonus points? What are bonus
The
points?
partial credit
I
question.
mean, it's only blue to you.
What if everybody has the same exact favorite color, but you see it differently?
We have had this.
We've had this discussion.
Jake Davis has a question.
What's like the main overarching conceptual question that we should know? Like, what are the main ones that like, oh crap, like just the main concepts.
Actually, I would react very well to compression.
I would say if there's any one concept I want you to learn from this class, it is.
Concrete acts very well in compression, but very poorly in tension.
There you go.
So why do we have compression?
So wait, what's the point of the
Now, hold on. Whoa. He asked a good one. Why do we have compression steel? Okay. To tie the rebar together? Because it's generally there, right? Look, you have tension steel, you have stirrups. Putting a couple bars up top will tie all the rebar together in one solid cage. That's point one. And point two, what benefit do you get from compression steel? Long-term deflections.
Decrease? Is that what it is?
It'll decrease them.
So I think it has a real prime.
Sir. Language. All right. Hold on. I'm going to do it because I feel like we're getting exhausted. Are you good?
Yes.
Mr. Potter?
Yeah, I know. I've
You-
never responded. You just kind
Are you good?
I guess I have to be.
No, I did. Your head was sort of doing this. In the back. You good? All right. Hold on, wait. Yeah, hold on. Did I pass sign-in sheet out?
Don't think so.
Sign out before you leave. That's all I got. I will see you all. Hey, 9:55. We're getting started.
I'll see you at 9.
Well,
I'm dedicated.
yeah, that's what it is.